In this lecture, we are going to study other X-ray diffraction method, which is powder method. This powder method is developed by scientists Debye and Scherer, and this method is the simplest and widely used X-ray crystallography technique. And in this method, the diffraction of monochromatic X-rays takes place from powder specimen. Here we are using the monochromatic X-rays, and so diffraction of monochromatic X-rays by powder specimen. Our specimen is in the powder form, and this is a great advantage as the polycrystalline materials can be examined without special preparation. The powder camera is used in this method. Powder camera, or it is also called Debye-Scherer camera, used. This camera is nothing but it is light, tight, cylindrical enclosure which holds a strip of X-ray film at its perimeter. Let me show you the diagram of that Debye-Scherer camera. Here is the diagram of the Debye-Scherer camera. What you see is the circular things. It is actually the cross section of the cylinder. Its shape is cylindrical, and the cross section of that cylinder is shown in this diagram. As you can see, there is a film at the perimeter. This is a dark black line, that is X-ray film, which is fixed at the perimeter of the cylinder. And this is the specimen, which is exactly on the axis of the cylinder. The position of the sample is on the axis of the cylinder. Then there is an entry port here and the exit port over here. Through the entry port, X-rays enter and they comes out from the exit port, which were blocked later on using the lead glass. And in this case, the specimen should be exactly on the axis of the cylinder. To bring the specimen exactly on the axis of the cylinder, there are two knobs over here, centering knob and the pusher. Using these two knobs, that specimen is brought exactly on the axis of the cylinder. So let's write what it consists, what this camera consists. As I said, this camera consists light cylindrical enclosure, and on perimeter of it, X-ray film is fixed. Then we have to prepare the sample, that is the specimen. The size of the specimen or the diameter of the specimen is about 0.3 mm diameter. Diameter of the specimen is around 0.3 mm and it is placed on the axis of cylinder. It is placed on axis of cylinder. Now how to prepare the specimen? Preparation of the specimen. It is prepared by grinding the grinding metal into fine powder. Size of the particle should be less than zero point 0.1 mm. So very fine powder is made by the grinding. Then it is filled, that is the powder, filled in borosilicate glass tube. Why borosilicate glass tube? Because borosilicate is transparent in X-rays. Or alternatively, paste of powder is made with adhesive Canada balsam is made, and that paste sprayed on wetted hair. It means that if this is the hair, on that hair, this paste, powder paste, is sprayed. And then this sample is placed exactly on the center of the cylinder, on the axis of the cylinder. So this is how the sample is prepared, and then it is placed on axis of the cylinder and then it exposed to the monochromatic X-ray beam. Here, let us take the example. Suppose monochromatic X-ray beam is directed at single crystal. Monochromatic X-ray beam directed at single crystal with correct theta, so that Bragg's law is satisfied. Then we will get one reflection. Only one reflection. Let me show you by drawing the diagram. This is the crystal, single crystal. This is X-ray which is a monochromatic X-ray, and this angle is theta, and this theta satisfies Bragg's law, and so we get one reflection here. We'll get one reflection. Now imagine here, imagine we rotate the crystal. What we are going to do? Rotate crystal around the direction of incident X-ray beam. Incident X-ray beam by keeping theta constant. Then what will happen to the reflected ray? This one is reflected ray here. And what happens, most of the X-rays go straight and we get the reflected ray here. Now what we are doing? Keeping theta constant and rotating the crystal around the incident X-ray beam. Then this reflected beam or this reflected ray will trace a cone with its apex at the crystal. Let me show that. So the cone is formed. This reflected ray will form a cone reflected ray then form cone with its apex at crystal, and this angle is theta over here. This is theta, this one is 2 theta, and this angle would be then 4 theta. This is also 2 theta. So this is what will happen. But in our case, we have the powder sample. What we have here is powder sample. And in this powder sample, because of the grinding, there are millions of tiny crystals which have completely random orientation. There would be millions of tiny crystals in this case with completely random orientation. Hence, let me write that. In powder, there are millions of tiny crystals with complete random orientation. And because of that, for every set of parallel plane, by chance, one or more crystals are there, one or more crystals will be in correct orientation. to satisfy Bragg's law in every direction. In every direction. Let me explain this. Here is the powder sample. Suppose we take one set of parallel planes. This is the incident X-ray. Most of the X-rays go straight. Then, in this case, if you take one set of parallel planes, then that set of parallel planes will have orientation, correct orientations in all directions. Every direction there would be by chance one or two tiny crystals which satisfies Bragg's law. So instead of getting one or two reflections, we will get a reflections such that that reflections will form a cone. So here we get cone. So one set of parallel planes will give us one cone. There can be another set, that another set will give us another cone. So we get here another cone for another set of parallel plane. So we get this second cone for the second plane. And since there are orientation in all possible directions, so some reflection will get back side also. So not only front side, but back side also we will get a cone. And so on. So for every set of parallel plane, we get one cone in forward direction as well as one cone in the backward direction. Then we have to remove this X-ray film and we have to develop and then fix it. We have to develop that X-ray film and then fix it, and we will get a film like this. This is the X-ray film, and in this there are 2 points over here and over here. Through this point, these are the 2 points over here. This is the 1 point over here, and this is another point over here. Through one, X-rays incident comes in, and through other, X-rays goes out. So these are the 2 points over here. And the distance between these 2 points, if r is the radius of that cylinder, then distance between these 2 points is pi r. This is equals to pi r, where r is radius of the cylinder. And around these points, we will get the cones. This is cone 1, this is cone 2, cone 3, and so on. Similarly over here, cone 1, cone 2, cone 3, and so on. So complete part of the cone we cannot see because our strip has a fixed width. that cannot accommodate the complete cone. So this distance pi r corresponds to angle 180 degree, and let's say this is length L1. This length L1 is corresponding to diffraction angle 2 theta 1. Then we can write this 2 theta 1 by 180 degree is equals to L1 upon pi r, or theta 1 is equals to 90 L1 upon pi r. So from this we can find the diffraction angle.